start off with Cavalieris Principle. We'll look at maybe an ellipsoid, or let's start with a cone. So I'm going to use a volume of a cone as an example. Now A has to be a subset of a rectangle for n of the interval for n of the coordinates, and some interval a to b. So R is a rectangle in Rn. And obviously AB is an interval in R. We're essentially now considering cross sections. Find AT to be the region in Rn, so in our rectangle, such that X and T are part of A. And suppose the area of parameter T will define as the volume AT. So this also has to be contented for all T's. And Cavalieris Principle says that the volume of A is just the integral of this area formula with respect to T as T goes from A to B. So for example, let's consider a cone, and I'm going to draw it kind of upside down. Hey, what's going on? All right, what do we want to talk about? Leibniz formula, Fubini's.
Leibniz formula? I haven't learned that.
It's one of your homework problems.
Okay. Like what did you prepare for this?
If nobody's here, I was going to do some examples of Cavalieris Principle, like we have to find the volume of the dome of the torus. That homework problem.
Oh, sure.
Well, I wasn't going to share that one while recording. There's Leibniz rule for Beanies. When can you exchange, put the limit inside an integral, that kind of stuff.
Sure.
Which one do you feel like talking about?
Can you say again?
What do you feel like talking about?
I looked at this week's homework.
Mm-hmm.
I don't know how to do most of the homework. I don't think my professor has covered this yet, so that's why.
Oh, I see.
You said I can do Leibniz formula.
Sure.
And what is the other first?
Leibniz formula, maybe Fubini's theorem.
What is that theorem?
So that's if you're integrating over let's say a rectangle.
Oh, you are not sure this.
I am too. Okay. Didn't this happen last time?
Yeah. Is there anybody watching you around?
Share the camera and write on the board. Easier that way.
You know what is product?
It gives you like pi or something, pi over 2.
Yeah, like there is one homework solved what one is product.
Yeah, I haven't looked at it, but it's I know you have to prove some stuff.
Yeah.
So we can go over Fubini's first.
Fubini's thing.
Which you know very well.
I'm not sure about that.
You can switch the order of integration. So that's a homework problem. It's like 3.6.
So for me, like, I read from calculus school, like when you change the order, like you need to do something, right?
Well, these are constant bounds, so not too much.
Oh, if it is not constant, you like.
Then you have, it's more, yeah, then you have to think about it more. Yeah, so you also have, to I guess really understand it, you have to understand uniform convergence, uniform continuity. But that's okay with it. So C to D and A to T. And then we define H And in a similar fashion, except the integral on the outside is with respect to y. So you can use the fundamental theorem calculus with the inside integral. Is that you or me? No, it's not.
Because my laptop and my iPads are all used. Maybe all that?
We'll check later. Okay. So we can do the fundamental theorem calculus here. This is, we'll call this big F, the antiderivative with respect to x at the upper bound minus big F. So we have to keep in mind the derivative of big F with respect to x is equal to f. So that's the fundamental theorem calculus. We're integrating with respect to x, so when we find the antiderivative, it's an antiderivative with respect to x. So now there's a well-known theorem, which is the content of problem 3.5, which you don't have to do. But if you're integrating a function of x and t, and x could be in a higher dimension, we're integrating just with respect to x over x's in some domain. If you want to differentiate g, then you just go ahead and differentiate inside with respect to t. So that's problem 3.5. And to be able to do that, you need the derivative of that with respect to t is uniformly continuous. Is uniformly continuous, which I don't know if the professor will talk about. But here all we have to do is it's an integral with respect to x, t is an independent variable. So you can just differentiate that with respect to t. Which is often used to solve integrals. Like, you know, the problem we have, I forget exactly how it goes, but you know the antiderivative, did you already solve it?
Oh, this is two sentences.
Yeah.
No, I haven't. I asked. Last Friday I was with Alan, and then I asked him for assistance, and then he couldn't even solve it, and then we struggled for a while, and then we stopped.
But sometimes what you can do is take advantage of this theorem, as long as it's uniformly continuous. This derivative is uniformly continuous. You can always introduce like a new parameter here. Like, I don't know where it goes, but something like this. I haven't tried it myself, but I've seen it done. You just introduce a t, new parameter, and now this becomes a function of t. And then what you can do is you can differentiate with respect to t. Here we have a continuous function and a closed and bounded interval, so this is going to, well, even after you differentiate, you're going to have a uniform uniformly continuous function. So you can now just differentiate the inside with respect to t. You essentially turned this integral into an integral of a rational function, just easy in principle, right? You do partial fractions. And once you get you integrate with respect to x, you plug in the bounds. So you're just going to be left with a function of t, right? And g prime of t is something. You can maybe recover g. And then all you to get the integral, all you have to do is evaluate g and t as 1. So that there's tricks involved with that. But it takes advantage of this. Oops. Right. So here you want to if you want to differentiate this with respect to t, but it's inside an integral, that's just with respect to some other variables. You can just go ahead and differentiate. So you can come up with your own problems like this where not solvable this way, but if you introduce a parameter, differentiate, becomes integrable, and hopefully if you know g prime as a function of t, maybe you can solve it. You can solve the g. Our integral is exactly g at 1.
So that integral actually equals to g of 1.
Yeah, g of 1 is the original. But I'm not sure if this is it, but it looks promising to me. But I don't know.
Okay, if
I don't know where to put the parameter t. I don't know here. But tricks like that are used. All right. Anyway, this theorem is important here because now we see that we have inside of here we have a function of y and t, right? I mean, this is just a function of y, but whatever. Here's a t and a y, right? So I can find g prime. So g prime, according to this theorem, you can just bring that derivative inside and differentiate with respect to t. And what if we differentiate this with respect to t? What are we going to get? Just they're changing variable names, right? T sub x. So you differentiate this with respect to t, and you should just get the original function as t1. So differentiating this with respect to t is exactly the same thing as the partial derivative with respect to x. So g prime would be keep the integral. You differentiate the inside with respect to t.
So that's f of ty, small.
Yeah. And then, of course, this does not involve t, so just see that we differentiate that second. And so now you can use fundamental theorem of calculus again, right? What if you like? This is going to be big F, I'll call it tilde, at the upper bound. Remember, it's an integral with respect to y. Where the tilde, big F tilde means the antiderivative of our function with respect to y. So if you differentiate this with respect to y, we just get little f. Okay, now on the other hand, here you can use the fundamental theorem calculus inside. So this is an antiderivative with respect to y. So the antiderivative with respect to y is f tilde. And then we plug in the upper bound minus, and then plug in the lower bound. And now we find h prime, but now we can use that other, the other fundamental theorem calculus where if you have an integral from a to t of a function of x, and you want to differentiate that with respect to t, that's just the function at t. Have you seen that? It's not too hard to show, right? This just needs to have an antiderivative. Right? If you integrate this, you're going to get the antiderivative of little f at t minus a. And then if you differentiate that with respect to t, this is the antiderivative, you should just get that. So this way of looking at the fundamental theorem calculus is like this form of the fundamental theorem calculus. You get the antiderivative and plug in the upper bounds. It's the same thing. Okay. All right, but here it's an integral with respect to x. Notice there is no y. I mean, we replaced y with specific numbers. So it's just a function of x. So you can see that h prime is just the thing you're integrating at the upper bound. So. Yeah, that's right. All right. So what that shows us is that whatever these two functions of t are, their derivatives are exactly the same.
So I always lost on that. How did you get from? How did you choose here?
Fundamental theorem calculus. All I did is I just we have a function of t, but it's an upper bound. So when I differentiate the center of the upper bound is t, I just plug it into the function. So now,
What happens to the lower bound?
what lower bound? Where?
We've got t in here.
Oh, as a lower bound is a number, it doesn't matter. So suppose the derivative of big F with respect to x is little f, right? We integrate from some number to t. This is a function of t. Differentiate, well, let's go ahead and do it the long way. Let's integrate. So you have the antiderivative at the upper bound, which is a variable t, minus the antiderivative at the lower bound. The lower bound is a number, we're assuming it's fixed. So if I differentiate g, here we're going to differentiate the antiderivative, so just get little f back. But this is a constant, so you plug in a specific number. So that's what happened. If you plug a into here, you just get numbers. Okay. So now we have g prime is exactly the same as f prime.
H prime.
And so if you anti-differentiate, they should differ by a constant. And that constant is easy to see. It has to be 0, because if you let t equal a in both instances, you get 0.
I'm sorry, how do you get the constant in this variable?
So if you have we have h prime equals g prime. And if I differentiate, you get h is equal to g up to a constant.
Yeah.
What is h at a? What is g?
Solving that equation.
Just from these two.
Zero, zero.
Yeah.
Oh,
And it goes from a to a.
Oh,
So that's 0. So we see that c has to be 0. So then h and g are exactly the same function for all t, so they're equal intervals.
that's cool.
So another common formula. I learned it first in both Boas book or theoretical concepts of physics or theoretical physics 3, 4, 11.
This is my next.
Oh, okay. That's where I first learned it. So it's 5 minutes rule.
Did you graduate from UCD?
I did it, yeah.
Oh.
I took that class with McKeown.
Oh, next semester my theoretical is.
Yeah, he started for like over 20 years. So.
And then my physics lab professor this semester is Dr. McKeown.
Yeah, he's been doing those labs for a while. As far as I know. So the Leibniz formula says, looks mysterious, but what if you have? It's a differentiation formula. So it kind of combines this theorem, right, where you can just differentiate the inside if you're not integrating with respect to the variable and its derivative is uniformly continuous, with the fundamental thing in calculus. So imagine you have some function of x and t. And you're integrating with respect to x, but the bounds are functions of t. So that's right. If we had just constant bounds that don't involve t. Well, let's just do that first. So just to right. So this is if you just wanted to know the derivative of this with respect to t, then according to our formula here, you can just differentiate the inside with respect to t. But what happens if the lower and upper bounds are functions of t themselves? So A, B, C, D, H, G, H. So what if these are the bounds of the integration? So you ultimately have a function of t. And so how do you find the derivative of this with respect to t? Well, you're going to have to use the chain rule, you see. So imagine, just for now, we have an integral from a to x. So this would be a function of t, correct? But we can think of this as, yes, but we can think of this as a composition, right? If we define, say x Oh, yeah, now I was right. Okay, so now, this is just this is a function of both x and t. Right? It's a function of t because there's this parameter t here. It's a function of x because x is an upper bound, so by changing x, you change the value. So, what if you wanted to then differentiate this with use? How would you find the derivative, yes, of this function?
Since it's only two variables, so I would find the 2 by 2 matrix like D1, D2,
Well,
or D2, D1.
let's just say that this is a function from R2, x and t, into a number, so R, right? So it'd be a 1 by 2 matrix. But what would be, of course, the first thing would be the derivative of our function with respect to x. Then we have the second, the other partial with respect to t. So what is the derivative of omega with respect to x look like? Well, it's just a fundamental theorem of calculus, right? We have the upper bound is x, and we would differentiate this interval with respect to x. All we have to do is plug that x into the u. Just amounts to saying the derivative of the u-type derivatives that we just integrate. And then the derivative of omega with respect to t, well, that's where you use this important theorem. And you just differentiate with respect to t inside then. So that would be just the derivative of that with respect to t. Integral from data x. The derivative of that with respect to t. All right, so now suppose that x is in fact not independent variable from t, but rather x is a function of t. So what additional theorem do you have to use?
F is a function of t.
X is a function of t. So we're going to say that x is h of t. Right, so then here we have omega, where x is a function of t. So now this is some function of t only. So you can reasonably ask for the derivative of this function of t. And how would we go about finding what that derivative is? Chain rule. You can just ignore this for a second, right? You've already done problems with this where you have to differentiate omega with respect to the first variable. And then chain rule, right? You have to then differentiate x with respect to t. Okay, then plus, you then have to differentiate omega with respect to t. Then times the derivative of t with respect to t is 1. Right. Well, and of course we're just, that would be the same as just taking this derivative and multiplying it by h prime 1 be like? So what is the derivative of omega with respect to x? It's just the original function. But at the upper bound, right? Times h prime. Plus, what is the derivative of omega with respect to t? Well, it's just this integral. Now you can use x instead of u in this case, I guess, right? Right. So that's exactly what's going to happen here, except both the upper and the lower bounds are functions of t. And if you'd like, you can just take a point between g of t and f of t and break up your integral if you'd like. Integrate g of t to some point in between. It's called k, this and that. Plus the integral from k to the upper bound. So now if you want to differentiate, well, first of all, we're going to write this as the negative of, right, so you can just use the theorem that we use here, the formula just used. If you have an integral from some number to the upper bound function of t, you want to differentiate that. You're going to get f at the upper bound, or x at the upper bound. And then times by chain rule, you have to differentiate by the upper bound. Plus the integral, where you now just differentiate the inside with respect to t. Why do I keep writing dt? That's so annoying. Okay. And then you would, to that, you just add the derivative of the next term, which again is just you're integrating at the upper bound times the derivative of the upper bound plus the integral. We just differentiate the inside with respect to t. So that's Leibniz formula. You're integrating with respect to x. There's this parameter t, but the bounds are also functions of t. And if you want to differentiate with respect to t, it's more complicated than just using the simple fundamental theorem of calculus. You typically put these back together, so you get what you would think fundamental theorem of calculus would be. All you do is differentiating, you evaluate this at the upper bound minus the lower bound. Then you also have to get these chain rules. But there's this additional factor, and it's essentially just the integral from g of t to h of t. And here you'd be integrating the partial derivative of f with respect to parameter t. So that was useful somewhere, either quantum or whatever. Right? You have like position and time. And, that's Leibniz rule. It's like, yeah, like combining fundamental theorem calculus with this theorem. We also had Cavalieris Principle.
Did you go to Beanies Theorem?
For a rectangle, that was, yeah, we did Fubini's for a rectangle.
That's Fubini?
No, that's where you can change the order of integration. That's Fubini. Right. In fact, in section 4, they have the Beanies Theorem. They actually essentially do problem 3.6 for you. I don't know if we have.
Hey, possible?
Ooh.
Is there a lecture? Please?
No, there's no lecture.
Okay.
No,
Help me, right?
are you in?
We just can find a place to study.
No, we're in. Oh, we're in the middle of something.
Okay.
They were looking for a room, I guess. Yeah, so yeah, Fubini's theorem we proved for a rectangle this way. That's all it kind of means. Also, so here's now your homework has this problem, but it's not the way he wants you to do it, so it'll be a different approach. But if you want to find the volume of a donut, kind of this, suppose this has radius b and I guess a. So a is the big radius and b is the small radius of the cross section. If you take a cross section here, you get a disk, correct? And we know the area of that disk. So that's going to be pi v squared. So that's the area of a disk. And then if you look at the central line, what's the length of that line or curve, whatever? What's the length of that curve?
2 pi a.
Mm-hmm. So if you take each cross section, you kind of like add it all up as you go along this curve, you would get 2 pi a. And indeed, this gives you the formula for the volume of a torus.
That's it?
Hmm?
It's just a formula, like,
Yeah,
so why do you say that one?
because the way it's defined in the book, the professor did it differently. They just did different cross sections. They took cross sections that look like this, and they found the area, the formula for the area as a function of, let's say, z. So this is the z-axis here. Given a certain z value, you can always take a plane and just get a cross section of the stone out, right? And it would look something like that. Just cut it. And so you can find a formula for the area of this angular region in terms of z. And then Cavalieris principle says that if you find that expression which gives you area, it's a function of whatever parameter, and you integrate as z goes from some lower to upper bound, that should give you the volume.
So this is a harder way.
Yeah, it's a little harder than this.
That's
Yeah, this was a little different because I think this is more standard, right? And also the way the book defines it.
so you said Cavalieris Principle?
Cavalieris, yeah,
Cavalieris. So is that in the book?
yeah, page 240.
So Cavalieris Principle is a short path of that integral.
It's you know, it's somewhat technical, right? But like, how do you find the volume of a cone?
Okay, so I find the cross section. Horizontally, I cut it and then find the cross section area. The function of the area.
So let's say this is height b and this is radius a, right? So you can come up with an equation of such a cone. So x squared plus y squared equals some multiple of c squared, where c is equal to b, and you want the radius of the circle to be a. So if you want the volume of this cone, you see that we can solve. So first of all, the theorem in the book says that as long as you can fit this in a rectangle, some sort, Cartesian product with an interval that acts like z or somewhere on the circumference. Here it's going to be z. Then you find a formula for the cross section in terms of z, say. So that the
So this go over a time.
well, this is the radius squared, right? So the area of a cross section is pi times radius squared. X squared plus y squared is r squared. So the formula for the area of the cross section is a function of z would just be pi times the radius squared, which is exactly this expression. That's a pi, right? Pi. So then Cavalieris principle just allows you to say that, okay, we're just going to integrate this as z goes from 0 to b. And that should give us the volume.
Why does that use this weird notation like a dv instead of dc?
dB, what do you mean?
So like there are some notation that uses dv instead of, for example, this one dv.
Oh, because it's a triple integral, so you have it's an integral over a region in space, so instead of differential length element like dx or differential area element like dx times dy, you have differential volume element dx times dy times dz.
Oh gosh.
Okay. All Alright, so then we can anti-differentiate this with respect to C. And indeed, we get the upper bound C is B. So
I over 3 A squared B.
which, if you recall, I don't know if you, right, if you have a cylinder of the same radius and the same height, we know the volume of that cylinder.
Yeah.
Pi A squared times B, right?
This is a third of that.
A third of that for formulas. So you can do the same thing for, like, if you want to come up with formulas for volume of ellipsoids.
Or volume of a sphere.
Sphere, yeah. And in fact, you can use that in higher dimension. If you want to, like, reduce a formula for the volumes of higher dimensional spheres, you can use Cavalieris principle, right? Because each cross section is just a lower dimensional sphere. Then you can just integrate over one of the variables.
Yeah, the more I learn about calculus, the more I see like the power of that.
Yeah.
That is powerful. That is really powerful.
Right. So you have problems like that, and several problems like that.
Oh boy.
You have one that's like two cylinders intersecting, and you're supposed to find the volume of the intersection.
Oh boy.
So that's going to be fun to
Have you
visualize.
looked at our exam one?
Hmm?
Have you looked at our exam one?
No, I just saw that one problem you told me about, but I haven't looked at it. Are the solutions available?
Like
Or is a test available?
like he handed out a test on it.
Uh,
Like if you want to look at the entire exam, I'm not sure later.
what else do you have on here? I think you have one problem involving Newton's theorem. Have you started the homework at all?
I finished the first problem at Edwards 3.1, one problem 1.2, 1.6, 1.8.
Oh, you finished that.
Like because I feel like whatever my professor comes in the lecture doesn't have so much to do.
Well, the homework is more computational than the theory.
Yeah. If he only talks about theory, okay.
But he did Leibniz formula. He didn't want to prove that.
We haven't learned that at all. None of this.
What have you learned? Like, you started talking about like areas, right? And integrals.
You can look at this is my lecture 18. This is last Thursday's lecture.
Yeah, but it's just like a bunch of theory.
Yeah, like last Friday I was trying to I was at the library and then I didn't see you. Like I meant to give you this notes.
But the homework is mostly doing some integrals, just computational stuff.
Yeah, and then
Proving some formulas, the Beanies Theorem in a rectangle and Leibniz formula.
that's very frustrating to me because he doesn't talk about any like he barely talks about computational stuff. He only talks about theory.
But there's a lot of computational stuff on the. Yeah, the Wallace one.
The Wallace one.
That's like, what is that? The Wallace one stuff.
Is it in section 4?
Did he do any implicit function theorem?
Implicit function theory? I don't think so. You mean chapter 3?
Yeah, chapter 3.
So, okay, I can give you this. In chapter 3, what he did is he spent one lecture on chapter 3.
Newton's, and
Newton's
he mentioned
method.
implicit and inverse function.
And he only let's see. We learned how to approximate the square root of 2.
Yeah, yeah. So there's a problem like that in the homework, right?
There is. Oh yeah, I did that one.
Oh yeah, but yeah, probably the first, number 1 on the homework.
Yes.
1.2
I did that. Yeah.
and 1.8. So it's implicit functions there.
Oh, you do want to look at that. Yes, it is some time. And that's pretty much it.
Percentage rules. Have you done a lot of double integrals, triple integrals? Not at all.
In calculus, you add some number. But in this class, not yet. And then I have trouble, switching the integral sign. Like when you switch integral sign, you have to do some changing.
You mean the bounds?
The bounds, yeah. You kind of change the bounds. Like if you change dx dy to dy dx, you kind of do the bound
Yeah. Why are you having trouble?
I didn't learn that well on that section in calculus.
Some famous ones. Good. Let's see what this will have to be. It's kind of want to choose a triangular region. So you want this integral to be not doable with respect to x, but you want to be doable with respect to y. So y will go from 0 to x. And then you can say x goes from 1. Or if we switch the bounds, then we have a problem. Right? So we integrate from with respect to y as y goes from 0 to 1, and with respect to x as x goes from y to 1. Okay, so that's the problem. So would you be able to fix this integral?
Yes. So what I have trouble with is not computing the integral. I have trouble with when we switch the bound, the bounds change.
Yeah. This is an example of that. Like you can't anti-differentiate e to the minus x squared. Like you don't know the anti. So sometimes you try switching the order of integration. So you typically just draw your region of integration. So y goes from 0 to 1. So these are y1. So y equals 0, y equals 1. And then x bounds are x equals y. And then x goes to 1. So x starts on this line and ends up on the line where x equals 1. So you're integrating over this region. So I don't think it's easy in general to switch the order of integration, right? You kind of have to have a sense of geometry, I guess.
So when you switch, it's more than the function.
Well, what are the bounds for x? Remember the x is on the, it's like the outside interval, so you have to have constant bounds for x.
That's from 0 to 1.
And y?
Y is from 0 to 1.
Because that would be a rectangle, right? If x goes from 0 to 1 instead of
0 to x.
y, then you're integrating over a square.
Is this from 0 to x?
Yeah. Y starts on the line where y equals 0, and then y increases till it hits the line where y equals x. But now the idea is that this antiderivative with respect to y is easy.
Use a negative x squared of y. And bound is from 0 to x.
So then you plug in the upper bound and the lower bound. So now then you can do the antiderivative with respect to both sides. Yeah, it can be tricky. So let's see. So if the bounds are from, let's say, x goes from 0 to 1, and y goes from square root of square root of x, let's say cube root of x. It doesn't matter what you're doing. How would you switch the bounds of the equation?
Do I need to graph this first?
Yeah. Unless you know something that I don't. At least it would help, right?
What does the square root and this cube root function look
Well, the square root function of y equals square root of x, and y squared is x, right? But it's only for positive y, so it's like a parabola on its side.
like?
And if y is the cube root of x, then y cubed is equal to x.
Or something.
Yeah, which one's going to be smaller? Square
Cube root.
is it?
Well, it depends. Like the 1 is the breakpoint. Less than 1 is going to be square root is going to be greater. And then
So cube root of a number between 0 and 1 should be bigger than the square root of that.
I think so.
So
We can test the number. That's the square root of 0.2 and cube root of 0.2. Square root of one point one, 1.4. Square root is
square root of x squared.
the square root of x. So the square root of I'm sorry. Square root is
Could be wrong.
0.44. 0.5. So square root of cube root is greater.
Yeah. So this would be the picture of the graph of y equals the cube root of x. And so now x goes from 0 to 1, and y goes from the square root of x curve to the cube root of x curve. So we're integrating over this sliver. Okay, so now if you want to switch the bounds, what do you do?
So x is still going from 0 to 1.
So the outside integral, now, okay, so when we integrate with respect to y on the inside, right, we think of like y doing this. So you see that y starts in this curve, and then it increases till it's that curve.
Yes.
But the outside bounds always have to be constants. They cannot depend on anything. They can't depend on another variable. But so if you're integrating with respect to x on the inside and y on the outside, for y we would have constant bounds. Y would go from 0 to 1. If you think of it as y starts on this line and ends up in this line, right? Wait a minute. Whatever. Okay, I just messed that up. Okay, from y equals 0 to y equals 1. Our region is between those two lines. Okay. But then, given some y between 0 and 1, when you integrate with respect to x, x is going to be changing, y is going to be fixed. So you're integrating from this curve to that curve with respect to x.
So y cubed to y squared.
Uh,
Lower bound is y cubed. And then
the lower bound is y squared, right? Oh, no, you're right. The lower bound is the cube root, so yeah, you're right. So x would be y cubed to y squared.
And then what goes in, like, shouldn't you have some number, like some, you have e to the negative x squared, should you have something here?
Sure. There you go.
So, and then to test this, these two always give me the same answer.
Yeah.
That's why I was very struggling with this integral.
Yeah.
Like switching the bound, like I don't know what to put on the what bound.
I mean, I don't know either. I typically have to draw. It's simple. It's double integral. Probably draw it on the side.
So how about triple integral? Like when you switch triple integral, does the bound change?
So yeah. Oh yeah. And you're going to probably be doing triple integrals using spherical and cylindrical, which is a good idea, right? If you're in physics. What else is there? I don't see anything else on the wall. 3.6, 3.7. Now that's just showing the function satisfies the differential equation. Oh, I know why he did that. So yeah, the reason he's doing 3.7, so this is a bit. So again, these are from physics, so basic functions, right?
Basic functions for physics.
I think so. Aren't all these solutions to differential equations pretty much physics?
What is basic function?
Well, they define it. It's defined as an integral, right? So that's a basic function. And then they have some factorial business, odd factorial. 2 is it plus 1 and minus 1 minus. And then, as part of the definition of the function of x, you have an integral from -1 to 1. And you're going to be integrating a function of x and t. With respect to which variable do you think?
ET?
Right.
Yeah, it says
Because it's a function of x, so if you're going to integrate a function of both x and y, you're going to be integrating the t out, so you have a function of x. So it's an integral with respect to t. What does that say? N to the negative half.
n minus 1 over 2.
Right. So now, if you want to know, you're going to have to compute a couple derivatives, so that's not going to be fun stuff. I mean, obviously, if you integrate out the t here, you're going to get a function of x, right? So you have a function of x times a function of x. So you're going to have to use product rule. But the question is then, what if you get around to differentiating this integral with respect to x? What do you have to do?
So is it like a partial of like
Yeah, that's right. So if you differentiate this integral with respect to x, but you're integrating here with respect to t's, not x. So you use that theorem. Now, clearly, this is a continuous function on the interval, on this closed and bounded interval. So it's uniformly continuous. So that would be the same as integrating. You just differentiate this with respect to x. No problems. So that's just practice in the theorem that's proven in 3.5, problem 3.5. Yeah, it's when we did this differentiation, we used the result from problem 3.5.
So when you take ddx, you mean the j sub n prime, right?
Yeah.
No, oh yes. And then it asks for j sub n double prime plus 1 over x, j sub n prime plus that thing. So I just need to find the j sub n double prime and then j sub n prime, and then compute, put it in, and that should get a 0. You have the column. You say it's 3.7, right? Yeah. So should I look for like I find double prime?
Yeah.
I find the first one, and then I let this, I put this.
Then plug it all in.
I should get it 0.
Yeah. It's a lot.
How much is this vector calculus?
This? Yeah, I mean, sure. I mean, I could replace x with a vector, like, it's like, yeah.
And like, is vector calculus multivariable calculus?
Well, no, so when they say multivariable, I think they do it on purpose to avoid using the word vector calculus. Because in 2415, you deal with vectors and stuff, and you deal with functions of many variables, and you see some of the theorems from vector calculus for R2 and R3, but they don't generalize, right? They don't generalize like this class does. So yeah, it's multivariable calculus, but then naturally that becomes vector calculus.
So would you say multivariable calculus class is like more advanced vector calculus class?
No, vector calculus I would say is more advanced.
Oh,
Because it uses, it's calculus plus all the linear algebra background.
so like the vector calculus class is even more challenging than this one?
I would say, I would say this is like part of, it's like multivariable calculus, but it's definitely part of vector calculus. Anyway,
I did cover most of the things.